Okay, I feel like I talk too much, and it might be a good idea that we start looking at some examples. Our first example involves the two-sample test for equal distributions. So that's quite similar to our motivating example where we are interested in whether group A and group B have the same distribution. Okay, so this example is going to use the chick weights data in R. So it's called chick WTS. I believe WTS stands for weights. So this data set is from the faraway package inside R. Here we will study the weights of newly hatched chicks fed different supplements. So we have two samples. X are samples, in other words, the weights of chicks who were fed soybean. And then Y is the samples or the weights of chicks who were fed linseed. We will let theta hat be the two-sample t statistic, which we know is sensitive to the difference in the means of the two distributions. And what we're going to do next is to compare the p-value from the t-test, which is assuming that the test statistic follows the t distribution, with the p-value from the permutation test, so without assuming the distribution. Okay, so let's first take a look at this data set and then perform the two-sample t-test, which you might be familiar with. If you haven't already, please install the faraway package by doing install.packages faraway. And then you will need to load the chick weights data inside the faraway package for this example. I have commented out the code for displaying the first few rows of the data frame chick weights. If you want to take a look at it, please uncomment this row and you'll be able to look at what the data frame looks like. So essentially there are two columns. One column corresponds to the weight of the chicks, and then the other column is a factor describing which type of supplement the chick was fed. I think there are a total maybe 5 or 6 total possibilities of types of supplements, but we will just compare two of them, soybean and linseed. Our X's are going to be the weights of the chicks who were fed soybeans. So there are a total of 14 of those. Our Y's are going to be the weights of chicks who were fed linseed, and there are a total of 12 of those. We can perform a t-test in R using the t.test function. All we need to do is to supply X and Y and indicate whether we assume that the two groups have approximately equal variances. And here are the outcomes we get from the two-sample t-test. The test statistic t is 1.32. There are a total of 24 degrees of freedom, and the resulting p-value is 0.199, which is close to 0.2. Well, this is not something, a hypothesis you would typically reject. So this is not a null hypothesis you will reject using many of the conventional p-values, say 0.05 or 0.01. So the t-test indicates that the chicks' weights for those who were fed soybean and linseed are, we do not have sufficient evidence to conclude that they have different means in the weights. And let's see what the permutation test tells us. So our first step in conducting the permutation test is always to compute theta hat. Theta hat is the estimator, or the test statistic computed using the original unpermuted sample. And this is simply the statistic, the t, 1.32, when we did the t-test. So theta hat on the unpermuted sample, or the observed sample, is t-test xy var equals true. And it's the statistic element inside. What we're going to do in permutation tests is to consider the different kinds of partitions of the union of x and y and see how our observed theta hat compares with those theta hat stars or theta hat j's obtained from the permuted samples. How many total possible unique partitions do we have for z equals x and y? Well, this is simply 26 choose 14, and that's equal to something really large. We definitely do not want to consider all of the possible partitions in this case, and we'll want to use the Monte Carlo approximation, and let's choose B equals 999. So here's the code for conducting the permutation test. First, we specify B is 999 and Z is the union of X and Y. Nu is the index set, indexed from 1 to the length of Z, in this case, 26. So the next step, what we want to do is to find the theta hat j's, which is theta hat evaluated at each of those possible partitions. We will again use the replicate function. We replicate this for a total of large B equals 999 times. And here's what we will replicate. We first find a random partition of Z. So what we first do is to create an element called perm, which is the shuffled indices of nu, essentially a permutation of nu. So this can be done using the sample function. If you do sample nu, where nu is from 1 to 26, size equals the length of x. So we are going to sample a total of 14 elements from this without replacement. Then this is the same as finding a random possible combination of x star and y star. So perm are a set of indices we will get. So it's a sample without replacement from 1 to 26. Our x stars are going to be the elements of Z corresponding to these indices. And then our y star is going to just be the remainders. So the elements of Z that are not sampled, not in perm. So our x stars and y stars is essentially a partition of Z. Based on this particular partition, we can find out what is the corresponding t statistic. So we know that we can get this by doing t-test $ statistic. And here, instead of doing x and y with the observed samples, we will do t-test x star y star, which is the partition that has been permuted. So what we will end up as the output of this replicate function is going to be a vector, theta hat j's, of a total of 999 elements. Each element is going to be the theta hat, in other words, the t statistic, evaluated at a particular partition x star and y star. Then we can compute the p-value as follows. We know that in this case, we want to do a two-sided t-test. So our t-statistics on either side are going to be considered. We will look at what is the probability of observing something as extreme or more extreme than the observed theta hat. So this can be done as follows. What we need to do is to compute the p-value, which is simply the mean of the absolute value, because we want to do a two-sided test of concatenated elements theta hat and theta hat j's. So theta hat is a one element, that's the observed one. And then theta hat j is the total of b theta hat j's that we have obtained from the total of b possible partitions. We'll evaluate whether the absolute value of this length 1000 vector, because we are concatenating one element together with the remaining 999, is greater than or equal to our absolute value of the observed value theta hat. So you can check that this is essentially equivalent. So by doing this, mean of this guy, it's essentially equivalent to the formula we have shown, which involves 1 divided by b plus 1 times the sum of the indicator functions. So the resulting p-value we get is equal to 0.207, which you can see is quite close to what we get from the t-test. And our conclusions remain the same. That is, we conclude that we do not have enough evidence to reject the null hypothesis. So earlier, our test statistic was the t-statistic, which is used for doing the t-test. The t-statistic is sensitive to the differences in the means of the two distributions. Sometimes we might also want to test for equal distributions. So not just looking at the mean, but looking at whether fx and fy are close. So this time, let's study the same data set, but with a test statistics that looks for any difference between the distribution fx and the distribution of y. And this statistic is known as the Kolmogorov-Smirnov statistic. We have briefly mentioned the Kolmogorov-Smirnov test, or the Kolmogorov-Smirnov distance between two distributions when we talked about bootstrap. So as I mentioned before, it's very useful for testing whether two distributions are equal. And that's what we're trying to do here. We're trying to see whether fx and fy are equal. The KS statistics is given by D, which is the maximum in the difference between the maximum absolute difference between the two CDFs, empirical CDFs, actually. So here, fxn and fym are the empirical distributions of x and y samples that we have. So because we have n samples of x, we call the empirical distribution fxn. And because we have m samples of y, we call it fym. So the Kolmogorov-Smirnov statistics is always going to be non-negative. And it looks for what is the point where the two CDFs differ the most. So let's first get the theta hat, or the D. That's the Kolmogorov-Smirnov statistic from our observed sample. This can be done using the KS test built-in function in R. When you do KS test, it implements the two-sample Kolmogorov-Smirnov test of x and y, and we also specify exact equals false. In this case, this is what we get as the output. You can see that it tells you what is the test statistic, the KS statistic, and it also gives you the p-value. So what is the chance of observing something larger than or equal to the D we have here? So again, we can see that the KS test tells us that there's no significant difference in the distribution of weights of chicks who are fed the two types of supplements. Let's see whether we get the same conclusion using permutation test. Again, we will sample a total of large B equals 999 partitions. What we want to do here is to suppress the warnings that are produced by the KS test. So when there are ties in looking for the maximum difference, then the KS test will return a warning message, and we don't want to print all of that when we do a total of 999 replications. So let's first set warn equals -1. So it suppresses the warning messages. Our first step is to compute the theta hat, or the D, from the observed unpermuted data. So like before, just like on the last slide, we do KS test of x and y, and we extract the statistic, which is the D over here. Next, we will replicate the partition for a total of 999 times to obtain the theta hat j's computed from each of the possible partitions. Things are quite similar to before. We first sample without replacement a total of 14 elements from the index set new. And then our X star will be the elements in Z that corresponds to the sampled elements, and the Y star is going to be the remainders. Then we perform the KS test on X star and Y star, but instead of looking at the p-value here, we extract the statistic, that is our theta hat J. Our theta hat evaluated at this particular partition X star and Y star. Our last step is to compute the p-value. But this time we know that D is always going to be positive. And larger D will indicate larger difference between the two distributions. And this time we will want to do a one-sided test where larger values of theta hat will support the alternative hypothesis. So we drop the absolute value this time. The p-value is simply given by the mean of theta hat concatenated with theta hat J's, a total of 1000 elements, greater than or equal to the observed theta hat. And we get p equals 0.455. So if we use alpha equals 0.05, then again, our p-value is larger. It's way larger than that. And we do not have sufficient evidence to reject the null hypothesis. So we cannot reject the null hypothesis that the two distributions of weight of chicks are equal. Okay, so there's one question you might ask. So for this particular example, our n choose n, so large n choose small n is going to be really large, so we want to do Monte Carlo sampling. So what if our n choose n is actually not that large and we want to look at all of the possible unique partitions? This is something you can get using the combination function in R. It's spelled COMBN. So this function can return all of the unique partitions, or in other words, the unique X stars, if we choose the total of n elements from the Z's. I'll give a toy example over here. So for example, if our Z is 1, 4, 2, 3, so our large n is equal to 4, and n is equal to 2, meaning that we have the first two, 1 and 4, corresponding to samples of X, and then 2 and 3 correspond to original samples of Y. Then we can get all possible X stars, which is 2 elements picked from Z, by using the COMBN combination function. So if you do combination Z2, it will return you a matrix. So I've stored it as parts. You can look at this element if you want. So for this matrix, each column is going to be one of the 4 choose 2 possibilities of X stars. So for example, the 5th column here, so X star, which is equal to the 5th possible partition of Z, will be given by, I think, 4 and 3. So once you have the X stars, you can find the Y stars by simply finding what is the complement. So what are the remaining elements in Z that haven't been selected into X star. So this can be obtained using the setDiff function, which finds you the difference between two sets. So for example, we know that Z is the vector 1, 4, 2, 3, and X star is the 5th column. So the 5th possible partition, which contains 3 and 4. Then our Y star will be the difference between the set Z and X star, and that will return us Y star that's equal to 1 and 2. So if you want to find all of the unique partitions and you want to exhaust all of the partitions, you can use the combination function to do that for you.